Chapter 3, I'll be talking about life, water, and life here briefly. Now, when you talk about water, water is made up of hydrogen and oxygen. Now, the kind of bonds, I talked about that in chapter 2 when I look at ionic bond. And I told you, I look at ionic bond and covalent bonds. And I told you that covalent bonds simply involve sharing of electrons, and there can be equal sharing of electrons or unequal sharing of electrons. When electrons are shared equally between two elements, it means they both share the electron equally, and that is called non-polar covalent bonds. And I told you that when electrons are shared unequally, it is called polar covalent bond. And that happens when there are two elements and one of the elements loves electron more than the other element. So oxygen is an electronegative element. It has high electron affinity compared to hydrogen. So when hydrogen and oxygen binds together to form water, hydrogen is not going to attract electron as much as oxygen will attract. So oxygen attracts more electron than hydrogen because oxygen is an electronegative element, whereas hydrogen is electropositive element. All right, so I'm going to write that here. So oxygen is electronegative element. It has high affinity for electrons, whereas hydrogen is electropositive. And have less affinity for electrons. Right? So because of that, hydrogen is going to attract electron less, whereas oxygen attracts electron more. And that's why you notice that when you see the bond, they don't stand side by side because they don't stand side by side each other. It does in a way that oxygen is attracting all the electrons to itself, attracting it. So hydrogen is just somewhere on the diagonals. All right. And so when that's what you see when you look at oxygen and hydrogen forming water molecules. So we say it's a polar covalent bond that makes it a polar molecule. All right, so that's why water is a polar molecule. You see that? Water is a polar molecule. All right. Now you see the overall charge is unevenly distributed, is unequally bonded. So polarity allows water molecule to form hydrogen bond with each other, and that is what you see here. So because they are polar, they are able to form hydrogen bond with each other here. So you see, here's hydrogen bond forming. Here's hydrogen bond forming between the water molecules. Here's hydrogen bond. Here's water molecule. Here's hydrogen bond forming between it. So between the oxygen and the water, between the oxygen and the hydrogen that makes water molecule is polar covalent bond. But between different two different water molecule is what we call hydrogen bond. So hydrogen bond is what connects two water molecules together. But covalent bond, polar covalent bond, is what connects hydrogen and oxygen together in a water molecule. All right. Now, so if you look at this, so there are properties of water that are very important, and those properties are achieved because of the kind of hydrogen bond that holds them together. Hydrogen bond is it's like a force of attraction that holds water molecules together. So we have the cohesive behavior, which is what allow water molecule to be together. So the cohesion is the reason that water molecules are usually like together. They usually stick together. If you are pouring the water molecule, it looks like they are flowing together. not detached. That's cohesion. So it's what holds water molecules to each other, cohesion. The ability to moderate temperature, that's also due to the bond between them. Expansion upon freezing, versatility as a polar solvent. The fact that they are polar molecule makes them to serve as universal solvents. I'll talk about that more as we go. All right, so collectively, hydrogen bonds hold water molecules together, and this is called cohesion. Cohesion results to high surface tension. That is why surface tension is the pressure that you see on water. That's why when you jump into a swimming pool, you don't hit the floor of the swimming pool as long as there's water there, right? You're going to be on the surface of the water. The water will do like the water is splashing because there's a force on it. Sometimes look like when you're even trying to swim, it look like the water is beating your hands, right? That's the way it looks like because there's a force on the water that prevents the water from just opening up, right? That's what we call surface tension. That's what makes it difficult for water to break and open up to you and let you hit the floor of the swimming pool. That's what we call surface tension. Now, cohesion contributes to transport of water and the subnutrient against gravity in plants. I'm just running through this chapter. I'm not doing like detailed study like I would. Adhesion is the property that holds the water molecule between the surfaces. So when you go to swimming pool, for instance, you will notice that water sticks to the wall of the container. Like this now, the water takes the shape of the container, falls with the wall of the container. So it's the attraction between water molecule and the container or the wall of the swimming pool. That will be adhesion. That's called adhesion's property, right? And that's the same thing that you have between water and plant cell wall, and that helps the water to be propagated to travel for transportation. All right. Now, water moderation of temperature. Water is able to absorb heat from warmer environment, warmer air, and it will release stored heat to cooler air. That's what water is able to do. So water absorbs heat from air that is warm, and it will release if that is already in there to the environment. You notice that when you think about it in the illustration of boiling water, now water can absorb or release a large amount of heat with only a slight change in its own temperature. Water is able to dissipate like that. Now, temperature and heat, kinetic energy is what we call the energy in motion, and potential energy is the energy at rest. So as I'm seated here now, I have zero kinetic energy because I'm not moving. All right. Because I'm not in motion, right? Now, kinetic energy associated with random motion of atoms and molecule is called thermal energy. Now, temperature represents the average kinetic energy of the molecule of in the body of matter. Now, thermal energy is the in transfer from one body of matter to another is called heat. So what we call heat is simply the thermal energy that is transferred from one form to another. So that is what we call heat. And the idea is this: if you remember that first law of thermodynamics says that energy can either be created or destroyed, but can be converted from one form to another. Now, second law of thermodynamics now says in the case of that conversion, when the conversion is taking place, there must be entropy, which is a state of disorder, and heat will also be released. All right. So the heat is what is released when one form of energy is converted to another form. Now think about it: when you buy your gas and you want to drive your car with the gas, what's going to happen? You are driving with the car with the gas that you bought, but that gas will automatically, which is chemical energy, is octane, which is a methane. It will automatically be converted into energy, motion. There's kinetic energy, motion. But in the course of that conversion into mechanical energy, in the course of that conversion, heat is lost into the environment. Your car generates heat that is lost, that you can't account for. So that is what the temperature and heat is. Right now, calorie is the amount of heat that is required to raise temperature of 1 gram of water by 1 degree Celsius. All right. It's also the amount of heat released when 1 gram of water cools by 1 degree Celsius. Now, the calorie on food packages are actually kilocalories. So they call it kilocalories. Kilo means 1,000. So kilocalorie is 1,000 calories actually. And joule is energy is also measured in joules. All right. And so you save 50 joules also of energy. So 1 calorie is equivalent to 4.184 joules. Now, specific of a substance is the amount of heat that is required or that is absorbed or lost for 1 gram of that substance to change its temperature by 1 degree Celsius. So it's the heat required or heat lost for 1 gram of that substance to increase temperature or change its temperature by 1 degree. So either one heat lost or heat gain to increase the temperature, heat gain to decrease the temperature, or heat loss to reduce the temperature by 1 degree for 1 gram. That is what we call specific if. The specific of water is then 1 degree Celsius. One is just is 1 cal, 1 calorie per gram, right? Now, water resists changing its temperature because of its high specific heat. All right, let's go. Now, the heat that water molecule have is traceable to its hydrogen bond. All right. Now, it's simple to just look at it that the heat that is required to break the bond or the heat that is released when the bond forms. All right. I'll just go ahead and look at evaporative cooling. Now, we talk about the heat specific heat, right? So the specific heat is a heat that is required to raise 1 gram of substance by 1 degree Celsius. So now let's go to heat of evaporation or vaporation. Heat of evaporation is the heat a liquid must absorb for 1 gram of that element to be converted to gas. Don't forget vaporization, to be converted for liquid to be converted to gas. That is what we call heat of vaporization. As a liquid evaporates, its remaining surface cools through a process called evaporative cooling. Right. All right. So floating of ice on liquid, water is less dense when they are in their solid state than when they are in their liquid state. So at 0 degrees Celsius, water molecules are locked into their crystalline lattice because they are less dense when they are solid than when they are liquid, right? Now, the hydrogen bond is what keeps the molecule far apart so that it makes the about equivalent to 10% less dense than liquid water. So water actually reaches its greatest density at 4 degrees Celsius. All right. Let's go. I don't need you to pay attention to that. All right. So I'll talk about this solution. Solution is when you mix solute and solvent. Water is universal solvent, and that tells you that liquid will always be solvent, or solvent will always be liquid. Now, solvent. So solvent cannot be solid. Solvent can be liquid. Solute can be solid. Solute can be liquid. All right, depending on if you are diluting an acid now, you're going to dilute it with a liquid. All right, if you are diluting, so there was a time that my daughter had, my wife was going to give my daughter orange juice, and we try to control what they're taking, right? So she had given a very diluted orange juice. So when my daughter was going to taste the orange juice, my daughter was like, she was 3 years old, and she's like, "Mommy, I don't want water juice. I want orange juice." Now, so water juice is what my wife produced after mixing orange juice with water. That's water juice. So when you see water juice at HEB anytime, please buy it. It's my wife's product. Now, so when you see the water juice is the solution, the orange juice is a solute, and the water is a solvent. So usually we use water as solvent. Water is usually called the universal solvent. That's why it's usually like water, water every time. But the solvent may not always be water. Like when you look at your some of the the hand sanitizer that we use now, it's dissolved with ethanol. That's the solvent. But water is the universal solvent. So that is solution. So a solution is a liquid that is completely homogeneous mixture of substances. So the solvent is the dissolving agent of the solution. Uh, the solute is a substance that is dissolved. An aqueous solution is one in which water is the solvent. All right. So if it is aqueous solution, that the solvent has to be water. But your hand sanitizer is not an aqueous solution, for instance, now because water is not the solvent there. All right. So look at this solution now. This is the solute, the powder inside, and that solute is sodium chloride, which is salt. Now it is going to dissolve in the water and it's going to dissolve. Sodium is out, sodium ion is out, NaCl minus chloride is also out, right? Now, water is a versatile solvent due to its polarity. Because water is polar, because it's made up of polar covalent bonds, it's a very uh, strong solvent. It's a good solvent. That's why it's actually we call it universal solvent. When an ionic bond is dissolving water, which is what you saw right now, when salt is in water, it's going to dissolve. All right. So when an ionic bond is dissolving water, each ion is surrounded by a sphere of water molecule, which is what we call the hydration shell. You see that? All right. So you see that here. All right, let's go. Now, when you say a substance is hydrophilic, it means it's going to dissolve in water. It's friendly with water. It has good affinity with water. That's why we say hydrophilic. So look at this. I'm going to annotate this. I'm trying to do this very shortly. And then, so if it has good affinity for water, we say it's hydrophilic. If it does not have affinity for water, meaning that it's fearful of water, hydrophobic. Phobic is fear. So if it's fearful of water, it's hydrophobic. So when you look at oil molecules now, oil molecules are hydrophobic because they have relatively non-polar bonds. They don't relate with water. They cannot mix with water. So we say they are hydrophobic. All right. So that's hydrophobic substance. All right. So molecular mass is simply I think chapter 2, I talked about atomic mass, how the nucleus is what determines the mass of an atom. So molecular mass is simply when you add the atomic masses together. That's actually what molecular mass means. So molecular mass is simply the addition, you see, is the addition of all the masses of an atom in a molecule. So let's say you have H2O, for instance. Now, if you have H2O, right? If you want to calculate the molecular mass, it's simply going to be 2H plus oxygen. So we know that H is 1. So it's going to be 2, 1. So I'm going to put a parenthesis here, right? 2, 1 plus oxygen is number 16. It's 16. The atomic mass is 16, whereas itself is number 8. So that will be 2 plus 1. 2 plus 16, which is going to make 18. All right. So 2 plus 1 makes 18. So this is the molecular mass of of water. Water is a molecule, so it's going to have molecular mass. If it is hydrogen alone, we're going to say atomic mass because it's an atom. Now, if it is oxygen alone, we talk about atomic mass. But if it is oxygen O2, then we're going to calculate its molecular mass, which is going to be 2 times 16. And that will be 32 gram per mole. So we say 32 gram per mole. All right. So this is going to be 32 gram per mole. This is going to be 18 gram per mole, for instance, now. So that is the way we calculate atomic mass. Molecular mass. All right. So the number of molecules are usually measured in molecules, where one molecule is about that molecules. Avogadro's number and the unit Daltons were defined such as this equals to 1 gram. So molarity is simply the number of moles of a solute per liter of a solution. All right. So that's simply how to calculate atomic mass. Molecular mass. All right, so I'm going to just focus on the few things I want to talk about. I'll go ahead and talk about acid and bases. Now, when you talk about acid and bases, think about it this way. If you break down water molecule, it's going to be broken down into H plus and OH minus. So if you dissociate this, for instance, we use the word dissociate. Okay, cool. So if you dissociate this, for instance, you're going to have H2O. So you dissociate H2O, it's going to give you hydrogen plus OH minus. Hydrogen plus is the same as, this is a proton. A proton, it's hydrogen ion or proton, and this is hydroxyl or hydroxide ion. So when you break down water molecule, this is what it gives you. When this increases, we say that acidity increases. When this reduces, we say that basicity reduces. So if I eat any food that gives me more hydrogen ion, that means my system becomes more acidic. If I eat food that gives me more hydroxyl ion, that means my system becomes basic. However, there are some segment of our system that helps to neutralize acidity, just the same way we talk about homeostasis. All right, so let's go ahead and look at that. Now, so water is in its state of equilibrium in which water molecules dissociate at the same rate as they are formed. All right, that is what I just showed you now. Now, okay, so this H plus is acidity, OH minus depicts basicity. So an acid is a substance that increases H plus. You see that? Whereas a base is a substance that reduces H plus or increase OH minus. So you want to look at it that way. So an acid is a substance that increases H plus hydrogen ion or reduces OH minus hydroxide ion. That is an acid. What is a base going to do? A base is going to increase OH minus or reduce H plus. So take note, so it can be two ways. An acid increases H plus and reduces OH minus. A base reduces H plus and increases OH minus. So strong acid and base will dissociate completely in water, whereas weak acid and bases reversibly release and are set back hydrogen bond, but they can still shift the balance between OH minus and H plus away from neutrality. Now look at this. This is where I'm going. Now let me do my annotations. Okay, cool. When you look at this, what we call the pH scale, it's based, pH simply means potential of hydrogen. And I'm going to write it here. So pH simply means potential of hydrogen. All right, that is pH. Now, what does pH mean? Usually you see pH that is usually in the scale of 0 to 14. So you see 14 here, you see 0 here, and you see 7 here. The 7 is the neutral. All right. Now, so in any aqueous solution at 25 degrees Celsius, the product of H plus and OH minus is constant and can be written as this. Now, that tells you that pH is actually not a table of 0 to 14, like 1, 2, 3, 4, 5, 14. It's a logarithm table. All right. So the pH of a solution is defined by the negative logarithm. You see that? It's negative logarithm, which is what you see a negative log of H plus concentration. All right. So for a neutral aqueous solution, the logarithm or the pH of that solution is 10 raised to the power 7, -7. So the pH is now going to be equal to negative of -7. Because pH is down to base 10 on the periodic table, it's base 10. Now, that means anything that has value less than 7 is acidic, and the higher it goes down the lane like that. And then anything that have pH of greater than 7 is basic. So we are basic because our pH is 7.35 to 7.45. So most biological fluids have pH between 6 to 8. Now, so you see this is the pH. So anything that is greater than 7 is is basic. So you see 7, 8, 9, 10. So that means 14 is more basic than 8. And when you come to acidity, 1 is more acidic than 6. All right. So if you come here now, you see the gastric juice in stomach is 7. Now look at it. There's a statement here that most, not all. Most biological fluid have pH of 6 to 8. Yes. But gastric juice in the stomach have pH of about 2. It's actually between 1 and 2. So that is not 6 and 8. But most of the time, we have between 6 and 8. So if you look at saliva, urine, is all between 6 and 8. Okay? Now, what is a buffer? I've talked about homeostasis. And so buffer system is part of the homeostatic mechanism that helps to maintain pH. So when we say buffer, sometimes you say, can I have $50 so that I can buffer my finance this month? Now, buffer is anything that helps to resist changes in pH. So anything that helps to resist changes in pH is a buffer. Anything that helps to resist changes in pH is a buffer. Anything that helps to resist changes in pH, it's a buffer. Anything that helps to resist changes in pH is a buffer. So so look at this now. This is H2CO3, H plus donor acid. Now, look at this. Up here, the forward reaction responds to rise in pH. So if pH increases, what's going to happen? This is going to be released so that it's going to accept the H plus, and so that the pH will not increase, this guy accept the H plus, and then the pH values reduces. But on the other hand, if there's a drop in pH, mean that it's now acidic. If there's any drop in pH, this HCO3 is going to capture the H plus that is there and form H2CO3. So again, I will take it. If there is rise in pH, pH rises. What's going to happen? This will dissociate so that it can open this up. But if pH drops, what is going to happen? This guy is going to capture H plus and then form HCO3. When it forms HCO3, it has captured some hydrogen ion from the system, and so that will reduce acidity. Because when this is not in the system, acidity reduces. The lower this is, so when this binds there, this becomes this, which is a buffer holding the acid together. All right, so acidification is human activities such as burning fossils, fuels, strengthening water quality. CO2 is the main product of fuel combustion, right? So about 25% of human generated CO2 is absorbed by the oceans, and CO2 dissolved in sea form, water forms carbonic acid, which is what we call ocean acidification, as you can see there. All right, I'm going to just skip that. All right, so that is chapter 3. Thank you.